Section 1.4.1 Key Exchanges, or How to Get a Shared Secret. The first asymmetric cryptography primitive we'll look at is the key exchange. The first public key algorithm discovered and published was a key exchange algorithm named after its authors, Diffie-Hellman, or DH. The DH key exchange algorithm's main purpose is to establish a common secret between two parties. This common secret can then be used for different purposes, for example, as a key to a symmetric encryption primitive. In Chapter 5, I will explain how Diffie-Hellman works, but for this introduction, let's use a simple analogy in order to understand what a key exchange provides. Like many algorithms in cryptography, a key exchange must start with the participants using a common set of parameters. In our analogy, we'll simply have Queen Alice and Lord Bob agree to use a square. The next step is for them to choose their own random shape. Both of them go to their respective secret place and, out of sight, Queen Alice chooses a triangle and Lord Bob chooses a star. The objects they choose need to remain secret at all costs. These objects represent their private keys. See Figure 1.5. Once they chose their private keys, they both individually combine their secret shape with the common shape they initially agreed on using the square. The combination results in unique shapes representing their public keys. Queen Alice and Lord Bob can now exchange their public keys, hence the name key exchange, because public keys are considered public information. I illustrate this in Figure 1.6. We are now starting to see why this algorithm is called a public key algorithm. It is because it requires a key pair comprised of a private key and a public key. The final step of the DH key exchange algorithm is quite simple. Queen Alice takes Lord Bob's public key and combines it with her private key. Lord Bob does the same thing with Queen Alice's public key and combines it with his own private key. The result should now be the same on each side. In our example, a shape combining a star, a square, and a triangle. See Figure 1.7. It is now up to the participants of the protocol to make use of this shared secret. You will see several examples of this in the book, but the most obvious scenario is to make use of it in an algorithm that requires a shared secret. For example, Queen Alice and Lord Bob could now use the shared secret as a key to encrypt further messages with a symmetric encryption primitive. To recap, 1. Alice and Bob exchange their public keys, which masks their respective private keys. 2. With the other participant's public key and their respective private key, they can compute a shared secret. 3. An adversary who observes the exchange of public keys doesn't have enough information to compute the shared secret. Note: in our example, the last point is easily bypassable. Indeed, without the knowledge of any private keys, we can combine the public keys together to produce the shared secret. Fortunately, this is only a limitation of our analogy, but it works well enough for us to understand what a key exchange does. In practice, a DH key exchange is quite insecure. Can you take a few seconds to figure out why? Because Queen Alice accepts any public key she receives as being Lord Bob's public key, I could intercept the exchange and replace it with mine, which would allow me to impersonate Lord Bob to Queen Alice. And the same can be done to Lord Bob. We say that a man-in-the-middle, or MITM, attacker can successfully attack the protocol. How do we fix this? We will see in later chapters that we either need to augment this protocol with another cryptographic primitive, or we need to be aware in advance of what Lord Bob's public key is. But then, aren't we back to square one? Previously, Queen Alice and Lord Bob needed to know a shared secret. Now, Queen Alice and Lord Bob need to know their respective public keys. How do they get to know that? Is that a chicken and egg problem all over again? Well, kind of. As we will see in practice, public key cryptography does not solve the problem of trust, but it simplifies its establishment, especially when the number of participants is large. Let's stop here and move on to the next section as you will learn more about key exchanges in Chapter 5. We still have a few more asymmetric cryptographic primitives to uncover. See Figure 1.8 to finish our tour of real-world cryptography. Section 1.4.2 Asymmetric Encryption, not like the symmetric one. The invention of the DH key exchange algorithm was quickly followed by the invention of the RSA algorithm, named after Ron Rivest, Adi Shamir, and Leonard Edelman. RSA contains two different primitives, a public key encryption algorithm, or asymmetric encryption, and a digital signature scheme. Both primitives are part of the larger class of cryptographic algorithms called asymmetric cryptography. In this section, we will explain what these primitives do and how they can be useful. The first one, asymmetric encryption, has a similar purpose to the symmetric encryption algorithm we talked about previously. It allows one to encrypt messages in order to obtain confidentiality. Yet, unlike symmetric encryption, which had the two participants encrypt and decrypt messages with the same symmetric key, asymmetric encryption is quite different. It works with two different keys, a public key and a private key. It provides an asymmetric point of view. Anyone can encrypt with the public key, but only the owner of the private key can decrypt messages. Let's now use a simple analogy to explain how one can use asymmetric encryption. We start with our friend Queen Alice again, who holds a private key and its associated public key. Let's picture her public key as an open chest that she releases to the public for anyone to use. See Figure 1.9. Now, you and I and everyone who wants can encrypt a message to her using her public key. In our analogy, imagine that you would insert your message into the open chest and then close it. Once the chest is closed, nobody but Queen Alice should be able to open it. The box effectively protects the secrecy of the message from observers. The closed box, or encrypted content, can then be sent to Queen Alice, and she can use her private key, only known to her, remember, to decrypt it. See Figure 1.10. Let's summarize in Figure 1.11, the cryptographic primitives we have learned so far. We are only missing one more to finish our tour of real-world cryptography. Section 1.4.3 Digital signatures, just like your pen and paper signatures. We saw that RSA provides an asymmetric encryption algorithm, but as we mentioned earlier, it also provides a digital signature algorithm. The invention of this digital signature cryptographic primitive has been of immense help to set up trust between the Alices and Bobs of our world. It is similar to real signatures, the one that you're required to sign on a contract when you're trying to rent an apartment, for an example. What if they forge my signature, you might ask? And indeed, real signatures don't provide much security in the real world. On the other hand, cryptographic signatures can be used in the same kind of way but provide a cryptographic certificate with your name on it. Your cryptographic signature is unforgeable and can be easily verified by others. Pretty useful compared to the archaic signatures you used to write on checks. In Figure 1.12, we can imagine a protocol where Queen Alice wants to show Lord David that she trusts Lord Bob. This is a typical example of how to establish trust in a multi-participant setting and how asymmetric cryptography can help. By signing a piece of paper containing, "I, Queen Alice, trust Lord Bob," Queen Alice can take a stance and notify Lord David that Lord Bob is to be trusted. If Lord David already trusts Queen Alice and her signature algorithm, then he can choose to trust Lord Bob in return. In more detail, Queen Alice can use the RSA signature scheme and her private key to sign the message, "I, Queen Alice, trust Lord Bob." This generates a signature that should look like random noise. See Figure 1.13. Anyone can then verify this signature by combining Alice's public key, the message that was signed, the signature. The result is either true, the signature is valid, or false, the signature is invalid, as figure 1.14 shows. We have now learned about 3 different asymmetric primitives: key exchange with Diffie-Hellman, asymmetric encryption, digital signatures with RSA. These 3 cryptographic algorithms are the most known and commonly used primitives in asymmetric cryptography. It might not be totally obvious how they can help solve real-world problems, but rest assured, they are used every day by many applications to secure things around them. It is time to complete our picture with all the cryptographic algorithms we've learned about so far. See Figure 1.15.